As you get used to electricity and dealing with individual charges, invariably you'll come across the next lesson here, which is on Coulombs Law. So what Coulombs Law tells us then is if you have two charges here, like a positive and negative, two positives, a negative and positive again, or perhaps two negatives, whatever the combination is, you know there's a force between them. Like, you know, for instance, using our adage that opposites attract, these two charges are going to want to fly into each other. These two charges are going to want to repel from one another, and these two charges are going to want to fly into one another once again. So what Coulomb's law tells us then, it tells us what exactly that force is that exists between two charges. It allows us actually to calculate how strong that force would be. So I've written Coulomb's law down here. You can see it right here. And what I'd like to do in this video is just go over the various parts of it to make sure you know how it works. Okay? So the first thing to note about it is, of course, it delivers a force to us, F, and the force is a vector. So it has a magnitude part and it has a direction. Let's talk about the magnitude part first. This portion of the law right here, which is K, Q1, Q2 over an R squared, is the magnitude part of the law. This tells you how strong the force is between two charges. So as you can see, it depends on four things. It depends on a constant K, depends on the amount of charge for charge 1, the amount of charge for charge 2, and it depends on the distance between the charges, which of course you have to square. So if you look up to say maybe this first example right here, we have all the ingredients here that we need, say, to analyze and use Coulomb's law. For instance, here's some positive charge here that we could note by Q1. Now, although I've drawn as looking maybe like an individual positive charge, it could be as much or as little charge as the problem states. It could be the individual charge in a proton, 1.6 times 10 to the minus 19, or it could be hundreds of nanocoulombs, whatever. All told, the amount of positive charge here is what Q1 would be. Q2 is the amount of the other charge. In this case, it would be negative. So there's your Q2 there. So it's a Q1 times Q2. And of course, the distance between them matters. So if this is the distance between them, we'll call that little distance, say, R or something like that. And that distance, of course, matters how strong the force would be. And as you can tell, since it's 1 over R squared, the closer the charges are together, the stronger the force would be. And the farther apart they are, the less strong the force will be. So that's the magnitude part here, there. K might be something new to here. It's a constant here. In fact, the value of K is really easy to remember. It just involves a couple of nines, 9 times 10 to the 9th, and the units are often sort of a big alphabet soup here, but it's a Newton meter squared per Coulomb. Oftentimes you can just drop out the unit, but you have to just make sure that everything else you do in this equation is in, say, coulombs here. Make sure this charge is in coulombs and this is in coulombs here, and make sure this distance here is always going to be in meters. Just be careful with those units there, because sometimes if you're working a textbook problem, you might be giving something like maybe 10 nanocoulombs, in which case you have to be careful to write 10 times 10 to the minus 9 coulombs before you plug into Coulomb's law in there. Okay? So you have a constant there, the amount of charge in the first case and the second case, and a distance squared between them. The R hat here, this part over here, it's a little R with a hat over here. This part refers to the direction of the force. And the direction of the force is often kind of confusing. And in fact, we have a whole other video on that. You can watch that. It's something that has a title of R hat. You should, because it sort of gives you an idea of what R hat is. But the reason why we have an R hat here is because of the following, the orientation that can happen here. For instance, I'll just draw a few combinations of pairs of charge here that you might be curious about the force between. So all these are supposed to be different combinations of charges like that. Maybe we'll get a couple negatives in here as well. Here's a negative charge and a negative charge, and maybe a positive here and another positive here. So in all these cases, I'll just sort of isolate them here. Here's two charges which are sort of vertical. Here's two charges here which are horizontal. Here's two charges here which are a little bit diagonal. Here's two charges here which are more diagonal. Two negative charges diagonal in a different way, and two positive charges which also have a sort of a diagonal bit about them. So the reason why we need an R hat is because these diagonals here can sort of point in any direction at any time. This one looks kind of nice because it looks all along the y-axis right here. This one looks nice because it's along the x-axis. Get my pen to write, the R hat would be right in there. This R hat's a bit confusing because it's sort of diagonal. It has sort of a component along x and y. So does this one. So does this one, and so does this one. So that's what the R hat is for. All of these cases here have a different R hat vector denoting the direction of the force. This one's R hat is straight up and down. This one's R hat is straight left and right. This one's R hat here is either down to the right or up and to the left, depending on what charge you're curious about the force on. This one, same way. All of these things here are the R hat, these different directions right here. And that's why, just generically in Coulomb's law, there's an R hat in there to denote we don't really know what the direction is, but you have to go in there and find it and fill in something for R hat if you want that full vector. So it's sort of like a placeholder for direction, and you can contrast that with something like just being a straight X hat along the X-axis or a Y hat along the Y-axis. there's only two cases in just the scenarios I randomly came up with here that have a direction along the x or y direction, this one and this one. So x hat would work on this one, y hat would work on this one, but all these other ones here, x hat and y hat wouldn't work. We need a more general placeholder. So instead of that, we just call it r hat, which is sort of a reminder to you that the direction is a bit unknown and you need to do a little bit of work in order to find that. So I definitely want to encourage you to watch this other video called r hat, which you can find in our collection to figure out what that does. So that's it in a nutshell there. It allows you to calculate both the magnitude and find the direction of the force between two charges. And so what I'd like to do then is just show you one more little thing to be careful of when you're using Coulomb's Law, which will hopefully help you avoid making some mistakes on problems at your work. And it's this. When you use Coulomb's Law, Q1, Q2 over R squared with an R hat right here, there can be some issues with the signs that are involved in these because, of course, Q1 and Q2 can have different signs. For instance, take a look at this problem right here. Suppose I have a charge here. This is going to be a positive charge right here. And say this is a positive charge right here as well. And what I'd like to do is I'd like to calculate the force on this charge here because of this one. So we know that like charges repel each other. And so what I'd expect over here, if this is charge 1 and this is charge 2 right here, I'd expect that this charge over here is going to push this one over this way. And I can call it something like the force of charge 2 on 1, something like that. And there's sort of an issue here now because if I go plug these into Coulomb's Law, since they're both positive charges, what I'm trying to illustrate here is like that K is a positive number, and whatever you plug in for Q1, like this charge over here, will be positive because it's a positive charge. This Q2 is a positive number, and of course the distance between them, the R squared right here, might be something like a centimeter or something like that, is also a positive number. So in other words, the number you're going to get here, you're going to get some big number if you calculate this, and the number is going to be a positive number. I should write positive right here to avoid confusion with positive charge. It's going to be a positive number. But there's an issue here because the force points to the left. And normally in physics, when we draw a Cartesian coordinate system, right is always positive and left is always negative. But here we have this leftwards charge being a positive number. But I thought that was a negative direction. It can cause some confusion. Here's another example of that. Suppose I have a charge that looks something like this. Suppose this is a negative charge here. And suppose there's a positive charge over here. Actually, let's make this the positive one and this the negative one like that. Okay. Now we know these two charges are going to attract each other because they're oppositely charged. And so what will happen here is, suppose I call this charge 1 and this charge 2. If this is the force here of charge 2 on 1 once again, so in other words, this negative charge, which could be an electron, is going to pull on this positive charge in the rightwards direction. So the force points to the right, F21. Now if you go calculate this F21, of course it's going to be the K again, and the Q1, the amount of positive charge here, and the Q2, the amount of negative charge here, all over the distance squared between them once again. And remember that R is the distance between the charges here. Here's another little issue to deal with here. This is negative charge right here, so it seems like Q2 here, Q2 is going to be a number which is less than 0. Q1 is going to be a number which is greater than 0. So if you look at the Coulomb's Law, K is a positive number, this is a positive number, but this is a negative number. And the distance squared will always be positive. So all told here, this can be equal to some number here, which is less than 0. But once again, you go, wait a minute here, a number less than 0. That means that the force, which is pointing to the right, is a negative number. And again, that's not where we're used to from our mechanics class, because usually in mechanics, if this is the XY coordinate plane, this way is always positive and this way is always negative. But here we have this force pointing, which we thought was the positive direction, but it has a negative value. So how are you going to make that all work out? Turns out the signs can be a huge headache for students to work on, and here's what I'd recommend. I'd recommend doing the following here. You use Coulomb's Law, but in a slightly modified form. Instead of using it just like this, put absolute value signs around the charges like this. Just knock out any of that sign business that might sort of confuse you here. So what you'll always get then is this magnitude part right here. Just always ensure that your magnitude is the number greater than 0, a positive number. How do you deal with the signs or the directions rather? What I recommend though is to use your common sense for the direction. Do not rely on the outcome of a calculation for your forces. So what you do in the following, let's go back to the one with a positive charge right here and a negative charge right here. Okay, as we just sort of did last time, this positive charge is going to get pulled towards the negative one that way. This is F21. This is charge 1 and that's charge 2 right there. So in order to make all this work out, we would head over to Coulomb's Law, and if we calculated this, if we use this slightly modified form here, the absolute value of Q1 times the absolute value of Q2 over R squared, what we're guaranteeing ourselves is this is going to be some number once again, and that number will always be a positive number, will always be greater than 0, because even though Q2 here is negative, we have the absolute value knocking out that sign. So we'll always get a positive number for the force. But now what we do, we just declare on our own it's a positive number and it points to the left. So we'll get some number here, the force will be some number, and here our CS, our common sense, will tell us it points towards the right. And if you want to know the force on this charge, say this arrow right here on the negative charge, this would be the force of charge 1 on this charge 2 over here. Look at that. It points towards the left. What do we know about this one right here? We can just grab a different color for you here to keep it clear. We know a couple of things. One, we know it's going to be the same magnitude. The force is going to be the same number because it comes from the same equation. The charges are still the same and the distance is still the same. Here's the R between them. It's still the same distance in there. But now what we'll do, we'll use our common sense again and say, oh, but wait a minute, they're two opposite charges. This one's going to get pulled that way. So we'll assign the direction randomly to be left. But see, once again, we always made sure this force number here was a number greater than 0, a positive number, which we're guaranteed to get if we put those absolute value signs in there. So the common sense will tell us then, before we proceed with the problem, whatever it may be, that the force direction is to the left. And we can make that correspond nicely with the way we draw our arrows or the way we think about it. Now you may manually assign a sign convention that maybe you're more used to from mechanics, where that way is positive, that way is negative, that way is positive, and that way is negative. So you can sort of go back to familiarity, and you won't let any negative signs from charges sort of mess up your force calculation. So that in a nutshell is Coulomb's law. I'll just wrap it up by saying it's very good. I'd like to encourage you to sort of think about the law that looks like this. Put the absolute value signs around the signs, and you can get your magnitude of the force from this part right here. The direction is kind of difficult to reconcile. We did a horizontal case here. Vertical ones are easy, but oftentimes the R hat can be more complicated. Please see the other video on R hat to get that nailed down. And that's it for Coulomb's law.